So what about sublimation then? But for sublimation, we're going to have to see it a little bit different. We will start with the solid. So we're starting with the solid there. And this is going to go into the gas. So for sublimation, you can say that the particles are going to separate more. So let me take. So it's going to be more like something like that. It's going to go from solid straight into the gas phase. So sublimation is going to be going from the solid to the gas phase. If we were doing a heating curve, then you will have something that will look like this. You will have your temperature going up, the heat is being added, and it will start like a solid. So this will be your solid, and this will be your gas. So the sublimation process is happening in between, where you're going to have the solid going straight into the gas. So this is a different process, and we can observe this possibly on solid carbon dioxide. You can also observe it on water when it's a little bit below 0 degrees Celsius. So it's a different process. So the process that we have are vaporization, or the opposite, condensation, melting, or the opposite, freezing, and then we have sublimation. And the opposite of sublimation, by the way, is called deposition. When gas particles come together to make a solid. And that's kind of the way we will describe the process of melting, freezing, and sublimation. So let's do this problem. Identify the states of matter for each of the indicated sections 1, 2, and 3. So based on this diagram, we can see that the first thing we have is a phase change happening at 0 degrees Celsius. Then we see another phase change happening at 100 degrees Celsius. So we can say, based on what I know, freezing point 0 degrees, boiling point 100 degrees, this got to be water. And we know that below 0 degrees, this would have to be a solid. So a solid will be, let me clarify that. So a solid will happen here, however, it's pointing to the plateau. So the plateau is where the melting and freezing happens. So that would be a solid and a liquid in equilibrium. Step number 2, that's when it goes from liquid all the way to liquid where it begins vaporizing. So number 2 is going to be just the liquid phase. But number 3 is another plateau or another horizontal. So that's going to be where you're going to have the liquid and the gas together in the first equilibrium. So that would answer the first question. What about the second question? Which section of the graph represent endothermic segments? So we said that when something melts, the molecules have to gain energy so they can start moving apart from each other and overcoming the intermolecular forces. So if we need to apply energy, then that's what we call endothermic. So an endothermic process is a process that requires energy. That's going to happen when we are warming up something. So going from 25 to 0 would be endothermic. If we are melting something, that's also endothermic. Warming up the liquid, endothermic. Vaporizing the liquid, endothermic. And superheating the gas. So every time we are adding heat, as we move to the right, the temperature is increasing. So this whole process, so based on that assessment, this whole process going on this direction is an endothermic process because it requires energy. So which in turn will represent the exothermic process. So the exothermic process is going to be when you release energy. And when you release energy, the temperature goes down. So the exothermic will have to be going in this direction. So if we're going on this direction, that means we are not adding, because we're going backwards now, we are removing heat. So an exothermic process, a process that releases energy, a process where we remove energy. An endothermic process would be a process that requires energy, a process where we add energy. And by following the x-axis, you know when we're adding, you know when we are removing. So more important than that, if we're looking at this graph, in this particular point, that's where it's going from solid to liquid. So solid to liquid is what we call melting. And this will be an endothermic process. So does it make sense that going from the solid to the liquid is an endothermic process? Yes, because once more, on the solid, the particles are very close together. They're going to have to start moving a little bit so that they will overcome the intermolecular forces and separate a little bit. That will definitely require energy. So melting is an endothermic process, the same as with boiling. If we go in that way, that's boiling, where the molecules have to even move farther away from each other, and they will not feel any intermolecular forces after that. So that will require energy. So that will answer this learning check. Let's see what else we have. What about here? How much energy is released? So we know that energy is going to be released. We can say that heat is going to be released. And we can say that the enthalpy is going to be negative, where energy is being released. So what are we talking about specifically? We're talking about release, how much energy is going to be released when 32 grams of water freezes. So freezes mean that it's going to go from liquid to solid. So the particles will have to slow down and allow the intermolecular forces to take hold and bring the particles together. So we are talking specifically about water. So that means the same way we use enthalpy of vaporization on the earliest lecture, what we use for freezing and melting is the enthalpy of fusion. And the enthalpy of fusion for water is going to be 6.02 kilojoules per mole. So the enthalpy of fusion just for water is 6.02 kilojoules for every 1 mole of water. Which means if we're looking for how much energy the process is going to release, so it's going to be negative because it's going to be released, and we're beginning with 32.2 grams of water, all we have to do is make sure that we end up with kilojoules, and we know that the enthalpy of fusion is taking place here because it's freezing. Since we're dealing with water, we know it's 6.02 kilojoules per mole. We know it's freezing, so freezing, the molecule has to slow down, so they have to release energy, so negative. So since we have moles, we're going to have moles in here so we can cancel them. And we're going to have the grams in there. So we're going to need the molar mass. Since we're talking about water, 1 mole of water equals 18.0 grams. So the grams cancel with the grams, the moles cancel with the moles, and since we're using the enthalpy of fusion, for water it's going to be 6.02 kilojoules. So for us to be able to freeze 30.2 grams of water, this much energy is going to be released. 32.2 divided by 18 multiplied by 6.02. So minus 11.4 kilojoules are going to be released when you freeze 32 grams of water. What about the next problem? The next problem is a little bit more complicated. On these problems, the question is how much heat is required. So we're going to be adding, so that's going to be an endothermic process. The first one, because it's released, it was an exothermic process. So how much heat is required to convert these many grams of ice, so we know that ice is a solid, right, at minus 12 degrees to water at 25. A problem like this, the best thing is to do a heating curve. Since we are doing an endothermic process, we're going to do a heating curve so we can visualize it better. So heat is being added. The temperature is taken in degrees Celsius and is increasing this way. We're starting with a solid. So that means water solid only happens below 0 degrees. And we are starting at minus 12 degrees Celsius. And we're going to go all the way to 25. At 25 degrees Celsius, room temperature, we know that the water is a liquid. So we're going to go from solid to liquid. So we're going to start at minus 12 degrees. We're going to start warming up, which means as we move to the right, we're moving up. So we're going to see something like this all the way to 0. Then on 0, it's going to be a while until it changes again. And then it's going to go up. And we are only interested all the way to 25 degrees Celsius. So just up till this point. So it's going to go from this point to that point. And the question is, how much heat is required? So we're going to have to calculate heat. I showed you 2 ways to calculate heat. Q equals the mass times the change in temperature times the specific heat. That's from chapter 3. And we also learned a few hours ago that you can also calculate the heat for a phase change, which is what happens on the horizontal line. And that's given by the mass or the moles times the heat of vaporization or the heat of fusion. So which one do we need here? We're going from solid to liquid. So that's going to be fusion, not vaporization. So we're going to use fusion. So notice that on the plateau, the change in temperature doesn't exist. The temperature doesn't change there. It's zero all the time. So you're gonna have to use that formula for that part. However, on this other part, the temperature is obviously increasing, right? And from this part here, the temperature is also increasing, which means we have a change in temperature. So we're gonna have to calculate this section here. We're gonna call that Q1. We're gonna calculate that section there. We're gonna call that Q2. And we're gonna calculate that section there. And we're gonna call that Q3. So the total energy is gonna be Q1 plus Q2 plus Q3. So Q1 and Q3 are gonna have to use this formula here because that's where the temperature change. Q2, we have to use this formula here because that's where there's a change of phase. So let's calculate Q1. So Q1 is gonna be the first formula, the mass, 5.88 grams, times the change in temperature is going from minus 12 to 0. So the change in temperature is 12 degrees Celsius, times the specific heat of the solid, the ice, which is 2.09 joules for every gram degree Celsius. So as you can see, the grams cancels with the grams, the Celsius cancels with the Celsius. So the only thing you're gonna have remaining is gonna be the joules. For Q number 3, same formula. The mass hasn't changed. However, the temperature went from 0 all the way to 25. So your delta T is 25 degrees Celsius. And for Q3, we are not dealing with the solid anymore. Now we're dealing with the liquid, which means we need the heat capacity of the liquid, which from chapter 3, I know is 4.184 joules for every gram degree Celsius. Grams cancel with grams, Celsius cancel with Celsius, so all you're gonna have is joules. So what about Q2? So for Q2, we're gonna have to be using the second formula because that's where the solid and liquid are in a perfect equilibrium. So Q2 is gonna be the mass, 5.88 grams, times the enthalpy of fusion, which is 6.02 grams. 6.02 kilojoules for every 1 mole. So this is the one where you're gonna have to change the grams to mole first. 1 mole, 18.0 grams for water, and that will give you, in kilojoules, that will give you Q3. So when you do all those calculations, that's the total energy required to take ice from minus 12 degrees and convert it to all the way to water at 25 degrees Celsius. So if you draw this cooling curve, you can identify, okay, this is my plateau. That's where I need to use formula B, which deals either with fusion or vaporization. You need to know what's going on. Solid to liquid, that's fusion. Liquid to solid, that's fusion. Liquid to gas, that's vaporization. Gas to liquid, that's also vaporization. One of them is positive, the other one is negative. So you know which one is gaining, you know which one is releasing energy based on what the particles are doing. So drawing a heating curve for this type of problems really helps you a lot. So with that said, go ahead and think about how we explain the movement of the particles and so on, and see if you can figure out 12.5a. Then you can do some math with diethyl ether. Remember, you have the formula with all the values right there. And after you're done with that, then you can do a problem similar to the one I did. Draw the curve first. And it's not really a curve, right? It's kind of like look like a steps or something like that. But it's a graph. You could draw the graph first. It could be heating, it could be cooling, depending on what's going on. And after you're done with that, you should be pretty familiar now with the melting and the freezing process. And we also talk about sublimation without going too much into detail, just understanding what it is. And you now know how to use calculation using the enthalpy or heat of fusion, which is either solid going to liquid or liquid going to solid. Solid going to liquid requires energy to get those particles moving. Liquid going to solid requires the particle to slow down, so they're going to have to release energy. And that would be it for this part of the lecture. When you come back, we will go deeper into understanding intermolecular forces. So until the next one, see you soon. Take care.